Welcome everybody to the control theory lecture of week 4. Here I will briefly discuss the mass spring damper system, but in a different context where we look at its mathematical derivation in the time domain, but also in the Laplace domain, and see what its response is to a simple input, a step function. So the mathematics will be was pretty much covered in the math videos on YouTube. I will have a separate presentation for that just to look up a bit, but now we will focus on the control theory. I would like you to prepare as many exercises from the workshop before you get to the workshop itself, and please look at these videos before you get to the lecture on Monday. Now, we were looking at the mass spring damper system, which is a simplified version of reality, and of course we only look at springs, dampers and inertia in the most ideal way, and the reality is of course often different, but this is a good approximation. Now if we look at the formulas, this is something we've seen before. We take Newton's second law and we apply the force related to the spring, the force related to the damping, and we have the mass times its acceleration. And of course there's a force applied to the mass. We can rewrite it like this bottom equation, and that enables us to see it as a differential equation. And it's not just any differential equation, it's a linear differential equation. It is second order and it has constant coefficients, and these constant coefficients make it something very important, which I'll discuss in next lecture or maybe week 6 in a bit more detail. It makes it time invariant. It doesn't matter when we perturb this system, when we apply the force, it doesn't change over time. The spring doesn't change, the damper doesn't change like you might see in reality, where the spring wears out or the damping becomes less, but it is the same system as time goes by. The response is different. If we apply more force, the system will behave differently. If we apply a sinusoidal force, it will behave differently, but if we do it now or in 10 years, the system will basically respond the same. Now what we haven't discussed yet is the other units of our parameters. Here we have, let's see, where are we? Here we have the damping coefficient. I sometimes use B, but sometimes we see C, and the spring constant. And we must hold in this situation is both that this differential equation is true, but the units must work out to the same as well. So what we need to do is figure out what the units are of these different constants, because every term in this equation must have the same dimension. So we must end up at the end at kilogram meters per second square. All right, so if we have that, we look at K and C separately. Here we look at K. If we take the units, kilogram mass over times squared, we have in this equation we have K times M. So the dimension of K times meters must end up like this, and this way we get that the dimension of K must be kilograms by second squared. Now if we look at the damping coefficient, we know that velocity has dimension meters per second. So here we had a term, the first derivative of the displacement has dimension meters per second, and that too must end up, if we multiply it by C, it must end up in kilogram meters per second square. So the dimension of the damping coefficient is kilogram over second. So now we have these units. Some software will check for units, but not all, and you have to be really careful that you don't start mixing dimensions, because then it would not make any sense. All right, so back to our mass spring damper system, and we look at the equations again. we look at this the strategy of investigating our system, because you don't always just want a plot in time, but we want to know what the behaviors of our system. So here we start with a free body diagram. We haven't drawn a lot of external forces in here, but we have an external force. We have the spring generating force, we have the damper generating force, and we have gravity generating force. And what we do is we start off by writing down our free body diagram, and from that free body diagram we get a differential equation. We make sure that our initial conditions are written down, and that defines our model. From that we can take the Laplace transform and substitute in our initial conditions, and we have moved from the time domain to the S domain, where S is a complex variable. That's not important right now, but we move from the time domain to the S domain. Well, what can we do with the system once we have it in S domain? And remember that a differential equation in the time domain translates to an algebraic equation in the S domain. So they're relatively easy to solve. Now, we isolate X, and we get this polynomial on X, because if we have an ordinary differential equation, a linear differential equation with constant coefficients, we will always get, where's my cursor? We will always get a fraction of polynomials. And this is nice because we can solve these. Well, we can use partial fraction expansion to generate blocks that we can use the inverse Laplace transform on. This is the this last bit. But if we have our function in the S domain, we can also look at stability, look at root locus plots, even Bode diagrams, and that will tell us something about the frequency response of our system and the stability of our system. If and the root locus plot is especially good to see. Well, what if our parameters change a bit? If the mass changes or the spring changes a bit, will our system still remain stable? All right, so this is usually the solution strategy. Now, if we look at one of the most simple inputs, just a step, there's nothing happening at time t is 0, and then from that we have a ramp to a certain force level. And this is just a unit step function. It's also called the Heaviside function, which is 1 for t larger or equal to 0, and 0 before that. Well, this is something we can use if we look at the input of our system. We have a constant force, we multiply that by the Heaviside function, and we get a unit step function with the force level F, which can be anything really, but we have chosen to write it as, we've chosen the value to be 1 Newton. So again, it's a unit step function, and we can see what happens in the Laplace domain. Well, if we have a step function, we take the table, we know that the Laplace transform will be 1 over S. Let's have a look at how that plays out. And yes, I know I'm sitting in front of the text that is written here, but it's simply what I've told you. It is a force multiplied by the Heaviside function. So we have our differential equations, and we take the Laplace transform. Initial conditions are 0, so we get this expression. Now, if we take the Heaviside function of the input of our force, which was a step function with step 1, we get 1 over S. Now, there's something in control theory which is called the transfer function, which is the ratio between the output and the input in the Laplace domain. And that transfer function will enable us to look at its properties, but also see what will happen if we have a control system controlling this system. So here we see, for example, the displacement and the force. The displacement is our output of our system, and the force is the input of our system, and the ratio between those two is this transfer function in S. Now we can solve this. We have solved for this, but what I'd like to show you is that we can also simulate this. This function here, the transfer function, we usually denote by the behavior of our plant, a system, which might have can be described as an actuator and a process, or just simply a plant. And this transfer function is usually denoted by a block in our block diagram. Now, the block diagrams can be all kinds of things, but mainly we have a block which has an input, which in this case was F, and an output which was X. Now let's have a look. This is an example of a piece of software called Xcos. It comes free with Scilab, which is a free piece of software, and I would like to show you a little simulation. But before we go to the simulation, if we look at the differential equation, or the transfer function here, 1 over 1 plus a half s plus 2s squared, this is something that we can solve, especially if we know the Heaviside function. Then we can isolate x, and we can take the inverse Laplace transform and plot it. So let's do that first. I'll run through this in a minute. If we were to plot that, we have the response, and we see that it goes up, wiggles a bit, but it settles finally on the force level that we set it to. Is this surprising? Well, yeah, if you have a spring and a damper, you might expect that you apply force, it could oscillate. This is actually one of 3, or actually many, types of behaviors that a system like this can exhibit. But just quickly back to the modeling software Xcos. What we see here is an input, and here we have chosen a step function, but here we can put in any type of input. We have our system where we show the transfer function, that is the ratio of the output of the input in the S domain. We have a multiplexer function that is nothing else than that we have 2 signals, and we interlace them together so that they are on one signal. It's not important here, it's just easier for the output where we have an oscilloscope to interpret 2 signals, because we're looking at 2 signals. One is the input signal, and the second one is the system response. Now, this was what we had solved before, and let me take you to the software itself. So here I have a couple of windows, and the main one I'm interested in is this window here. I can run the simulation, and I've run it before, but you can see the output of the system. Now, this modeling software is very powerful because it will allow me to do a number of things. One is I can change the time that the step starts to, let's say, 5 seconds. I can run it again, and because it's what's called a linear time invariant system, if I apply the input 5 seconds later, I will get the same response only 5 seconds later. I can change values of my transfer function here. I will just change the let's just change the damping. We'll increase the damping by a factor 4. It updates it, and we can see that the behavior is already completely different. There's a bit of overshoot where it goes above the reference force, but you see that the damping will dampen out a lot of these oscillations we had before. So this is very, very, very powerful software, and it's also free. Now, well, we've done this live. Another piece of software which I'm particularly a fan of is MATLAB, and it is unfortunately by no means free. It has been the go-to software for control theory and numerical analysis. It's been around for decades. It is still widely used in industry, and we have a couple of licenses at the HVA, so you could play around with it. There are student licenses as well, but it is a very, very powerful tool for modeling mechanical systems, pneumatic, electrical systems, doing all kinds of data analysis, also data science things. And yeah, it's just something well used in the industry. I have here some videos about MATLAB, and I'll let you watch these by yourself, and I will stop this video for now, also because of the beeping in the background. This is just a short introduction to control theory, block diagrams, and the use of the Laplace transform when analyzing systems. If you want to have a look at Scilab, search for Scilab and Xcode, have a play around with it. We might be using it a bit more when we look at different properties of systems. But this is it for now, and I'll see you next week.